Welcome to the Mana Car by Matt, Allie, Nick, and Anna. Allie unfortunately is sick, so she can't present with us today, but she helped us a lot. So thanks, Allie. Without further ado, here is our car. We got a lift to drag ratio of negative 5.418 newtons. As you can see here, we ran the car at a mesh size of 4, 5, 6, and 7, and the mesh size did affect the lift to drag ratio that we got. However, since our car is so smooth, the mesh size of 7 actually helped us a lot, and we chose to use that value when we ran all of our plots. To come up with this design, we started from square one. So in the top left corner, you can see Allie's car, the first car that she made, which actually got a lift to drag ratio of 0.1. So it was generating lift instead of downforce. In the top right, you can see the first car that Nick made, which has a very low pressure at the top and a lift to drag ratio of negative 1.4. And then on the bottom right, you can see Matt's first car that he made, which got a lift to drag ratio of negative 1.55, and actually integrates a few features like a spoiler. But in the bottom right, we have the first car that I made, which got a lift to drag ratio of negative 1.64, and actually integrates the first diffuser that we tried, which helped us a lot in our final design. So when we went back to the drawing board and designed again, we started working with SolidWorks surfaces. So to the left, you can see Matt's second car that he designed with SolidWorks surfaces, which has that very smooth look, which got a lift to drag ratio of negative 3.67. But unfortunately, this car does not have wheels, so it is not within the parameters of design. So we had to go back to the drawing board, but we found out that we really liked using surfaces from this design. And to the right, you can see Nick's car, which follows more of a box design, has the spoiler, the split surface in the front, spoiler in the front, and a diffuser. But for some reason, we just could not surpass negative 2.6 with this car. So we had to go back to the drawing board and start with another body design. So with our design approach, most of our initial designs did not have diffusers, but when we began adding diffusers, we learned that a gradual upsweep was best. We also learned that the diffuser angle has a sweet spot, and if the angle is too big, it actually hurts the ratio more than helps it. The front face of our cars also began more as a convex shape, but when it was flattened, the ratio improved. So we then went further and created a concave shape, which improved the ratio even more. We decided to sweep up the back of the car to integrate the spoiler into the body rather than separating the spoiler from the body. And we created wheel guards to lessen the sudden change of direction that the air was flowing underneath the car.
And like Anna previously showed, we learned to utilize SolidWorks surfaces so we could better mold the body of the car the way we wanted to. This allowed us to lower the sides of the car and create a tall middle section for the passenger compartment with a divot to create more laminar flow. And then we created a small nozzle in the front to increase the velocity of the incoming air and to channel the air under the car and create a sort of venturi tube. And then we finished off eventually with just adding a bunch of fillets underneath the car, on the sides of the car, and around the wheels. This assisted in creating more laminar flow and greatly contributing to our higher number. And then this is the final version of our car. Combining the two second generation cars that were previously shown, we came up with our final design, coming up with a lift to drag ratio of an incredible negative 5.418. We integrated similar body shape of a Le Mans car with the surfaces feature in SolidWorks. And then on this slide, you can see our sizing images. And we chose to keep our passengers side by side as opposed to behind each other. This would maximize the area of the front slope. And we decided to keep the engine long ways for a more streamlined approach. And then in the pictures, you can see we show see-through projections of the car, showing the 35 by 35 by 50 passenger compartment, and then the 40 by 30 by 25 engine block. And in this slide, you can see our graphs relating drag force and lift force to the vehicle's velocity. And then you can see the exponential increase in the magnitude of lift and drag forces as the velocity increases. And then this is a plot of our lift to drag ratio versus the vehicle's velocity, ranging from 50 miles per hour to around 200 miles per hour. And then here is a horsepower plot, ranging from 50 miles per hour also to another 200 miles per hour, where you can see that exponential increase as well.
So this is our first pressure plot of the car. This is the front isometric view. And you can see there's quite a bit of air stagnating on the front. But like Anna said, we purposefully made our front concave. So this allows for a really good lift to drag ratio. It almost acts as a spoiler in the front of the car. And there's also quite a bit of air stagnating on the back of the car, but that's fine too, because it's still just a spoiler back there. And then there's a blue region up top where there's a lot of air moving quickly over the top. And a lot of our design was actually revolved around trying to minimize this blue region, which is creating lift. But we found that this shape was pretty optimal. We tried to round it out, but it just kept on increasing the air. So we left it looking like this. And then here's our rear view. We added this hole into the back, right at the end of the diffuser, into the back of the car. This dragged air through the hole and up into the back of the car where the wake is, so we could hopefully disrupt the wake and low pressure region behind the car. And then here's our underbody view of the car. So we obviously have that giant low pressure region, which is great. We tried to, increase the area of that region as much as possible. I think this is one of the main reasons why what Anna was talking about, the gradual angle increasing of the diffuser works, because you want to keep that area down there to help out with that low pressure suction effect, versus if you just sweep it up really, really quick, then the diffuser sort of steals a lot of that suction effect away from the body of the underbody of the car. And then here's a cut plot of the velocities. As you can see, we do have a pretty large wake, but that's obviously unavoidable. And the hole definitely helps there. You can actually see where the hole is and how it takes away some of the blue region by replacing it with green higher pressure, or green slower velocity, which creates higher pressure. And then you can see the high velocity through the underbody and through the top of the car in those red regions. And then here's a wireframe view of our car up top. And then down low, this is just an interesting thing we saw after we were fully done design of our car and testing, that our car basically models the shape of a teardrop, which is the most aerodynamic shape. But it has two spoilers, one in the front and one in the back. And the front spoiler basically deflects all of the air away from the part of the teardrop that would be generating lift, because it has that sort of positive slope where if the air connected with it, it would deflect down, causing our car to lift up. But we sort of negate that part of the teardrop, but hold many of the benefits of its streamlined effect. And then for the water tunnel testing, we analyzed a 1/20th scale model. So we'll show that calculation right now. So for the velocity, we did a simple Reynolds number comparison where we equated the Reynolds number of the air and the water to generate the same flow field. And we calculated, we replaced the density and full scale car characteristic length and the viscosity, and we got a new velocity number for what it would be in a water tunnel. And then we use that number to calculate a new force, just using a proportion method where we said that the density went up by 1,000 to 1.225, and the area went down by 1/400, because our 1/20th scale model causes a square for the area, so it's 1/400. And the velocity goes down by that decimal ratio right there. So that causes our force to go down by that final ratio on the right. This led our force in the water to be 6.62 in the downforce direction and 1.221 in the drag direction. And that's all. Thank you for watching our presentation.